Hello, y'all. Welcome to lesson 132, my DP chemistry curriculum. Today we're going over structure 2.4.4. This covers polymers, how they are large molecules or macromolecules made from repeating subunits called monomers. We will describe the properties of plastics in terms of their structure. Now, you'll notice this is a much earlier unit, but I like to do it after we've covered organic chemistry, as we can kind of gather a little more information and make some better predictions about what's to come based on what we already know. So, just to start us off, polymers are generally what we think of as plastics, but they are molecules or macromolecules, macro meaning big, and molecules referring to molecules. But polymers are molecules made of repeating subunits called monomers. It's basically exactly what I said in the intro. Now, this comes from the Greek meaning many parts. So poly means many, mers refers to parts. So mono just means one part. So a polymer is made of multiple monomers. Now, when we look at polymers, generally when we think about plastics, these are often long chains of hydrocarbons. So basically, we're just looking at repeating hydrogen and carbon, which are organic compounds, as we've learned so much about, still covalently bonded. So let's take a look at one of the most common polymers around our world. This is polypropylene. Now, polypropylene, just the name alone lets us know a lot of things. Poly is once again going to refer to multiple. Multiple what? Well, propylenes. We know the prefix prop comes from three carbons. We know ene refers to a double bond. So when we look at the actual structure of polypropylene, we can see many repeating subunits. So the real structure of polypropylene just looks like this. Carbon bonded to hydrogen, bonded to carbon, bonded to CH3, bonded to carbon, hydrogen, carbon, CH3, carbon, carbon. I'm just kind of going in whichever way I feel like. And all of these on the bottom are going to be hydrogen. What you'll actually notice is this is a repeating set of units. In fact, I have drawn three repeating units or monomers, the monomer being that three carbon chain. I'll highlight it for you. Three carbons and we get prop. This does come from a structure that does originally have double bonds, which we'll learn about in the next section. That's where the ene comes from. But basically, we just have this repeating structure of like propanes bonded to each other. And this is polypropylene. Now, we can better describe it referring to all the subunits. And for that, we just use brackets. We put our bond outside the bracket. We'll put another one here, CH3, H, H, H with an N. And this refers to N repeating units. And this is how we refer to most polymers, just by N repeating units. And we can draw it as such with the bracket around one monomer and a little N subscript to say it continues on and on and on. So this is all a polymer really is, a repeating section of covalently bonded carbon and hydrogen atoms that extend forever. Now, I said earlier we often think about plastics, so let's talk about plastics a little more, as they're one of the most common and useful materials in our world. I guarantee no matter where you are, there are at least five different things that are made of some type of plastic polymer, so we use it everywhere. Plastics generally refer to polymers that can be easily molded or extruded things you can do with polymers. And some of the very common ones, other than the like polypropylene you saw, would be like polythene, or sometimes we call it polyethylene. So I'll use the notation that we just learned here. Carbon, carbon. So this is one of the simplest ones. In fact, it is the simplest polymer. Uh, and this is polythene or polyethylene, um, or yeah, polyethylene. So then we also have a very common one that you use in like tubing and piping, and this is polyvinyl chloride or PVC. You've probably heard of PVC piping. Polyvinyl chloride, PVC. And you can see there's some differences. Mainly in this, we have a chlorine versus a hydrogen. But when we look at plastics, we learn that they have many different properties that are useful for our daily world. And we'll go through each one of these. First, they're flexible. Well, the reason they're so flexible is that these are just long chains held together by intermolecular forces. So if we look up here, I've got a chain of three, but you can imagine it going on for hundreds and hundreds. And if you put another chain right on top and another chain right on bottom, those chains attract each other through intermolecular forces. And because they're only held together by intermolecular forces, we can generally associate the strength of those forces with the flexibility. So a lower or a weaker IMF is equal to a, oops, not a, is equal to a more flexible plastic. So, for example, polyvinyl chloride has that chlorine, and that chlorine is what gives PVC that very hard texture, hard appearance, that property. It can still be bent, it can still be molded, it can still be extruded, but it's overall more hard than other plastics because of that chlorine. Uh, Furthermore, in addition to flexibility, we also have some very decent durability. Durable. It's durable for very much the same reason. Individual chains are hard to break. So those long chains are nothing but carbon and hydrogen bonds, which are decently strong in comparison. So it's hard to break those, which gives it overall durability. This also does lead to the fact that this doesn't degrade well. So you'll hear a lot about microplastics, and that's because while we can separate those chains, we still get these long individual chains that are very hard to break down and very hard for organic living creatures to break down. And so we end up with these long hydrocarbon chains that are just one long polymer of a plastic, and it's very hard to break down. So it's very durable. We say it is moldable, meaning you can shape it. And as many of you will probably know, that when plastics warm up or they heat, so they can be heated. And what happens is the IMFs break, allowing the overall structure to reshape. So once you break those IMFs, it's becomes a liquid of these long chains that you can move around. And then as they cool, those IMFs will reform in whatever shape it's in. And that's how we can mold it. You may have heard of something like injection molding plastics, where you heat it up, put it into a mold, and let it cool, and then it becomes that shape. Um, very much like casting metal. So furthermore, plastics are lightweight. Lightweight is because the chains don't actually get that close. Uh, the IMFs holding chains aren't very strong. So the chains are loosely packed. This is what gives many of the other features, such as the durability and flexibility, well, more of the flexibility. And because they're loosely packed, it is a less dense structure. Therefore, it's lightweight. And when I say less dense, I'm talking about in comparison to things like metals, which are very dense as they're very tightly packed. Lastly, we know that these are actually great insulators of both heat and electricity. However, with heat, again, it's only until the IMFs break down. But they're great insulators, and one of the reasons you can see that is there's no moving electrons for electricity or particles for heat. They don't really conduct because they don't have anything to conduct that. So these are some of the main reasons that we use plastics, and they all come from that chain structure. Now, when you're comparing plastics, we generally look at properties versus their IMFs. And so when we're looking at properties versus the IMFs, let's take a look at some common polymers so we can actually compare. And we'll look at the monomer structure. So one of the most common polymers is, like we said before, polyethylene, coming from the monomer of ethene. It's our simplest one. Then we have PVC, polyvinyl chloride. It's very close. It comes from chloroethene, but it's much harder, and we know that from the chlorine. And then we have one of the strongest polymers we've ever invented, Kevlar. We use it for bulletproof vests. And yet this is just a plastic, just like the others. Now, this one starts with a benzene ring structure, goes to a ketone, and we still get our chlorines. But it's not just this structure, it's actually repeating of this structure plus another structure that has amines. So again, this is why I like to do it after organic. We get to look at these different structures and actually recognize what's there. So in polyethylene, we only have London dispersion forces, which hold our chains together. It's very loose. It's a very easy to rip and tear plastic. It comes in pretty much the form of like plastic shopping bags, or if it's higher density, milk cartons. But overall, because of the LDFs, it's a very weak plastic. You can rip a shopping bag, and with enough strength, you can probably rip a milk jug too. Now, PVC is used for conduit, used for plumbing, and PVC does still have London dispersion forces. It has more because it has a higher mass as well, but it also has dipole-dipole interactions. With that chlorine there, that chlorine is going to add to that dipole-dipole interactions. Now, lastly, Kevlar, we know it has LDFs a heck of a lot more than the first two. It also has dipole-dipole. We can see that in a couple places between the carbon and oxygen and carbon chlorine on both sides, between the carbon nitrogens in the benzene rings. And in addition to all of that, it also exhibits hydrogen bonding. Because of that, Kevlar is so much stronger. It is going to be a lot more durable. It is going to be stronger in almost every way. However, we are then going to be trading off things like flexibility and moldability when we start adding those extra intermolecular forces. So hopefully the little bit of OChem we already have helps you kind of see all this a little bit more clearly. We're going to go into how do we take our monomers and turn them into polymers in our next unit, and have a great day.